Thank you, Walter. Uh, Welcome, everybody. And we just wanted to welcome you to our second, as Walter mentioned, the second Tech Talk in a series of presentations that we have laid out throughout the year. This year was we're doing a quarterly, and we hope that FY22 will be doing this, every month. The intentions of the Tech Talk was to try to bring the community together in topics of interest that are relevant to the Department of Energy Office of Environmental Management, but also to our colleagues throughout the globe that are undertaking the same type of decommissioning and environmental remediation projects as the Department of Energy. So we hope to keep the community informed, engaged. Again, we want the knowledge to be transferred to make a bridge between colleagues that may be working in similar topics, and perhaps start new relationships with other researchers across the globe. So with that, I'll turn it over to the presenters. Today we have the topics of robotics, and Dr. Dwayne McDaniels and Mr. Glenn Zune will be presenting. So Dwayne is, a FIU, and Glenn, he is with Washington River Protection Solutions, our partner in crime in terms of the development that we are doing in support of the Hanford tank farm. So with that, I'll turn it over to Dr. McDaniels.
Thank you, Leo. Let's see here, do the swap. Can everybody see the presentation full screen? Is that full screen?
Yes, yes.
Okay.
Very good.
Perfect. All right. So welcome, everyone. The title of the talk is the use of robotics and nuclear applications. And again, I just reiterate, if you guys have questions pop up during the talk, you'd be more than welcome to interject and ask, or you can save them to the end or throw them to the chat. I think Walter will keep track of those. My name is Dwayne McDaniel from FIU. Glenn, you want to say hi real quick? Glenn from WRPS is here as a counterpart. And then we also have some other FIU folks that might chime in as well as we go along. Glenn, you want to say hello real quick?
Hi, I'm Glenn Soon from WRPS. I'm part of the Tank and Pipeline Integrity Group. We take care of the tanks, and yeah, been good to have FIU's help in developing some robotics to aid us in inspection and applications.
Thanks, Glenn. All right, so we've got a couple of preamble slides. Some of you may be aware of FIU and some of you may not, so I'll just go ahead and kind of go over some background information about FIU. I guess depending upon what year we're talking about, our enrollments tends to fluctuate a little bit. We tend to increase. So at one point we were a top 10 university. I think we're a top 5 university now in terms of enrollment. We're also a top tier research institution as designated by the Carnegie R1 doctoral universities, which is an indication of the highest research activity. Our engineering programs are all ABET accredited. We are a minority serving institution, and we are tops in the U.S. in terms of awarding bachelor's and master's degrees to Hispanic students. We've got some other statistics shown on the right. Again, I think the numbers are a little bit fluctuating, but we're a little over 57,000 now, 10,000 employees. We have 11 colleges and schools and quite a number, over 200 programs in terms of bachelor's, master's, and PhDs. A little bit more background. This talk is primarily about our robotics and how that's going to serve the nuclear industry and DOE in particular. And all the work is done by most of the folks here that are listed in our robotics lab, where we've got the PIs, myself and Leo Lagos, a number of research assistants, Anthony Aparna, Mackinson, and Shervin. But the real work is done by the students listed below here in the DOE fellows, Dan, Sebastian, Joel, etc. And then we have some other robotics folks that participate. And in the right there, you can kind of see sort of an agglomeration of a lot of our tools that we've developed over the years. And so this work is supported by a number of different groups: DOE EM, NETL, LM, DOE NEUP, MSIPP, as well as NSF. So with that, we'll kind of start the process of talking about the robotic tools that we're going to look at today. Just as an overview, we're looking at systems that we're developing here sort of from scratch, conception, if you will, to try to get to a deployable state and to assist engineers in understanding, generally speaking, the integrity of the infrastructure within the DOE complex. We have some other projects as well that are related to providing the robotics as they provide physical assistance to workers with significant physical requirements. But this is a little list of some of the tools that we're going to talk about, some of the projects that we're going to talk about. We've got a number of different systems aimed at Hanford's tank farm to assist them in terms of their inspections. We have a magnetic miniature rover that we'll talk about first, and then we'll move over to a ultrasonic transducer mini rover, then shift gears to a 90-degree rover, marsupial crawler. And then we're really going to shift gears and just look at infrastructure inspection, some wall climbers and pipe climbers that we're looking at for Savannah River, some general mapping and surveillance of EM facilities, and then lastly, I'm a robotic manipulator used for assisting in glove box operations. This is just a little outline, kind of goes over all of the tasks that we're looking at. The next part, since we're going to shift gears and go right into the inspection of the Hanford tanks, I'm going to pass the microphone over here to my colleague, Glenn, soon. We'll give you just a little bit of description of the tank farm. And Glenn, whenever you're ready, you just let me know and I'll go to the next slide.
All right, cool. So if you guys are not familiar with the Hanford tank farms and the Hanford site in general, Hanford was created to support the American nuclear weapons and nuclear materials production, World War II era. As you can see, we have a lot of waste on site here, 177 total tanks, a lot of single tanks that you see there. They were constructed in the early 40s. They are, a lot of them are leakers or assumed leakers. The double shell tanks were then constructed to be the next wave of safe storage. They were constructed in the 60s and the 70s, 80s. The newest tanks are the AP series, constructed in 1986. And some of the older farms, however, are already past their design life. So we can go ahead and go to the next slide. So if we're looking at our DSTs, you can see there's some overhead pictures of the construction up right there. And then there's the current state where the tanks are all buried underground, and there's only the support buildings on top that you can see and access. So in these tanks, there's a number of risers, leak detection pits, access areas, and some tanks do have pumps. And you'll see in the diagram, the tank is full of liquid and sludge. So there's a supinate layer, liquid air interface, and a sludge layer at the bottom. So the sludge layer is kind of what it sounds like, a mix of solids and liquid. And the chemistries vary from tank to tank. And you can see in this picture, and I don't know if we probably have a better one coming up, but there is a leak detection pit, that a drain line goes under the tank to the secondary liner, the external of the secondary liner there. The internal secondary liner has a air slot pattern that's called a refractory, and that is an insulator between the secondary liner and the primary tank. And those slots are what we use to send a probe, a rover, or some robotic inspection tool down to inspect the bottom of the primary tank. So all these areas are very difficult to access. They exist under a tank that's, buried 60 feet underground, and access is only available through small riser ports in the top shell of the tank there, ranging anywhere from 24 inches to 4 inches. We only have two 24-inch risers to access the tank annulus space. We can go to the next slide. So here's another picture of our tanks, and it looks like we have a couple annotations here. So part of the problems that we face with inspecting our primary and secondary liners are, of course, access. So access to the tanks are somewhat difficult. Again, there are riser ports that access the annulus, and the robotic equipment must fit through those riser ports. That's why we come to develop the mini magnetic rover, because it can fit through a 4-inch riser, which we have much more plentiful access using 4-inch risers. And it'll magnetically couple to the sidewall of the tank, be able to drive down the sidewall and access the air slots underneath the tank. Here we can also see the tank foundation and the number 2 there. So the leak detection pit is our only method to take a look at the bottom of the secondary liner. So the leak detection pit and the leak detection pit drain line in a couple of these tanks have, as shown here, vertical risers that go to different spots at the bottom of the secondary liner. The newer tanks have excuse me, a slot cut, so they're not individual vertical risers that intersect with the secondary liner bottom. So a larger swath of the bottom of the secondary liner can be seen. And number 3 is a ventilation pipe system. So that is part of the obstruction inside the annulus that we have to deal with when we're navigating circumferentially around the primary tank of the with our robotic tools. So that makes the necessity for having a smaller robotic crawler, because we can't quite drive around the entire circumference of the tank from our larger axis risers. So I don't know if anybody has questions about that. I think that's all we got to talk about.
Thank you, Glenn. Okay, so with that description, here's a slide here that talks about our miniature rover that Glenn just mentioned. That is a magnetic miniature rover, very small. It can fit within these slots. Dimensions of the slots are very challenging, very small. And what you can see here are 2 different configurations of those slots that sit in the refractory pad that cool the bottom of the primary liner. There are, if I remember correctly, Glenn, there are 2 tanks that have the sort of the concentric circle approach, and one of those is out of service. And then we have the remaining ones with the more friendly tree structure. Is that correct? I think the other 25 or so.
That is correct.
Yeah, okay. So the mini rover was designed primarily to go through the refractory structure that you see on the right. And it has, these little soft, 20 to 30 degree type turns that it goes through, but the slots are very, very challenging. At the top they're sort of, at the top they're about 2.5 inches wide, and at the bottom of the channel they're about an inch wide. So very, very, very tightly constrained area to have to navigate through. And you can see in that picture next to one of the rovers, some debris, some refractory material sitting at the bottom, making it even more challenging if you're trying to navigate along the bottom of the refractory. So our approach was to come up with a tool that basically rides upside down on the bottom of the tank, navigating or magnetically attaching itself and navigating through those slots, and being able to get through to the central plenum is ultimately the goal. So it has to go through a couple of those little turns, but the unit itself has a very, very strong pull force, and of course anything that goes into these tanks has to be tethered, so we have to be cognizant of that. And there are other challenges as well. There's a little bit of radiation, not too bad, elevated temperatures, weld seams, and of course scaling and buildup and corrosion that we're going to have to contend with as we continue to refine the tool. But it is essentially a small little tool. You can see on the right the control box that we have for it, and you'll probably recognize some Game Boy type controllers that are used for the folks to navigate with this, and then a big screen so that you can see, you can drive this blind yet see what the mini rover is showing you. We have front and rear cameras for the system as it navigates through. The idea though here is for this particular tool to be able to navigate the slots and assist in terms of understanding what the state of the health of the tank liner, or the primary liners, that is. So with that, I'll switch to the next slide. And in order to evaluate the tools that we have, not just for the primary liner, but for all the other systems as well, we've developed what we're calling a full-scale sort of sectional mock-up, if you will, of the DSTs. That includes the primary liner, includes the secondary liner, it includes the refractory in between those two, it includes the annulus space. It even has the drain line that and the ventilation lines that were sort of the challenge to navigate around the side of the tank that Glenn mentioned. And then you can see our construction. So on the far left, you can see sort of how those refractory slots look like. We have a couple pairs of those refractory slots as they reach to the central plenum, and then the white pipe representing the air supply line. And then in the middle, you can see the primary liner sitting on top of the refractory pads, and then there's a secondary liner sitting underneath that. And then on the right, you can see without any of the refractory or the liners, you can see what the drain slots look like, and that was mentioned as well. And that's an interesting challenge, because what you can see there at the very close to the central plenum, it's about 2 or 3 inches deep, but as it goes all the way out to the outer radius, it goes to around, I think it's like 12 or 13 inches. So it slopes down so that if there is any leakage, then it will drain into that drain pit that was mentioned before through the drain line. So you can kind of see how much of the tank we're representing here with this mock-up, in that the little sort of schematic there on the right. You can see about what 8 feet of that looks like for the rest of the tank, but at least we have a good real scale representation, which is about I said 8 feet wide, about 37.5 feet long for at least with the primary liner, and we've got around 2.5 to 3 feet of annulus space there as well that we can fit into. And that's the big challenge, is that there are very limited risers in the annulus space, more 4-inch that Glenn already mentioned. And so our particular crawler can then be deployed through those small risers, and then probably get access to more locations than maybe systems that require the 24-inch deployment risers. So with that, now this presentation is littered with videos. There are tons of videos in here, and what we did was with our miniature rover, you can see the miniature rover there moving in the video, going over weld seams. We developed a test plan in conjunction with WRPS that looks at the unit's ability to traverse weld seams, as you just saw there. The test plan kind of evaluated the system's durability in terms of how robust the system can be, or is, the ability to go over corroded surfaces. You can, to the far right, you can see worst case scenarios there of some of the slots. So we've got in the middle there at the bottom, you can see the corroded surfaces picture. That was one of the surfaces that we used to run our robotic system on to evaluate its ability to handle the corrosion. And then there's different types of weld seams as well, whether they're more conventional rounded weld seams or just sort of random type weld seams with not necessarily super quality weld seams. You can see there, making sure that our systems can go over those types of weld seams. So the test plan included weld seam traversal, corrosion traversal, durability testing at elevated temperature, mind you. We'll talk about that in a second, as well as an emergency retrieval. And I'm thinking there might be one other test I'm forgetting, but we'll probably touch base on that in a second here. We go to the next slide. And then you can see this is our miniature rover in the camera navigating through the tight confines of those slots, and kind of see what it looks like as we come up to maybe, you can see here a little plate. I guess that's the end of the video. And on the left, what you can see here is the when we did our durability testing, we used some fans, heated air that blew heated air through the slots to get the temperatures up to around 120, 130 degrees Fahrenheit, and allowed us to test the unit multiple times, having it traverse back and forth from the central plenum, from the annulus to the central plenum in a heated environment. I think it was over 20 times, making sure that it could handle that. And then in certain cases, we did emergency retrieval. So if it did get stuck or fail, we could retrieve it, make sure there was a way to retrieve it so it wouldn't be stuck in the unit. And then in the middle, what you can see there is you can see how that mock-up looks. We had to insulate it with material to keep the heat in as much as possible to get elevated to those temperatures. So it was a pretty and then we have it mapped there. You can see, I think, 4 different thermocouples that would allow us to sort of monitor the temperature, making sure we're getting a distribution that was representative of the tanks. And we worked with WRPS in terms of getting that all set up. And understanding what we need to do to make sure the system would be feasible to work with. Anyway, moving on to the next slide. So that's the end of the discussion for our mini rover. I guess I'll pause here. I don't know if anybody's got any questions. You can shout them out if you do. If not, then we can move on to the UT sensor sister rover. I'll pause here for a second. No questions. Okay, so along with our miniature rover, our first miniature rover that we just discussed, really is designed to inspect the primary liners of the tanks and identify areas of concern. But what we would like also to do is to be able to quantify any damage or any thinning in the tanks. And so with that, what we've done is we've developed a sister rover that has an integrated ultrasonic transducer with it. And what you can see here is that it's a little bit further behind in the development, but it's just sort of these are some bench scale tests. We're getting ready to go through the process of developing a test plan and evaluating that in our mock-up as well. But so here are just some videos of some of the bench scale tests that we did for this system, and that includes also navigation of weld seams and those types of things. The rover does need, with the UT sensor and with the potential scaling or corrosion or whatever it may be on the surface, we do need to have the ability to be able to brush clean the surface, abrade the surface, so that we can get a reasonable measurement from our UT sensor. And so this is, let me see if the video shows here. I think we already showed this video, right? Kind of running over the weld seams. Show that again. We have another video over here that demonstrates the concepts of the brush onto the right. The brush has a linear actuator that pushes it down and then spins it and rotates it so that it can abrade off any material on the bottom. The idea, and you can kind of see how that can clean a specific area. We have to work since the actuator and since the UT sensor and the brush are not co-located. We do have to worry about cleaning an area and then being able to navigate to that particular area and taking the measurement with the UT sensor. So here's some videos, additional videos of the ultrasonic system. Let's see here, make this play. So this shows you sort of the kinematics of how that UT sensor is deployed. It's pushed down. It has to have some level of contact force, mates with the surface, takes a measurement, and then can come back up. So I give you an idea of the description here. On the right, we show the unit. You can kind of see here. I know it's difficult to see. There's a number here, and if you look, I kind of see my pointer here. Reading around 15 or so there. But that's where we're taking the measurements. So this is the unit actually being upside down. We do have a water couplet that we're using when we take our measurements. So you can see a little bit of water dripping out. We're in the process of changing out the pump, but it comes up. You can see the numbers now changing. Reading was that roughly 6 mils or millimeters rather, something on that order as it takes the measurements, showing the general functionality of the system. Okay, so as Glenn mentioned earlier as well, the AY101, which is one of the tanks that has the different refractory slots configuration. If you look up to the bottom right, you can see how those might be a little bit more challenging. There's about, I think it's 17.5 feet of straight section before we hit a first concentric circle. And then we have to make either a right or left turn, 90-degree turn. And then shortly after that, a couple more feet after that, you're going to have to make another turn as you navigate yourself towards the central plenum. So this particular inspection tool, which we're calling the 90-degree rover, is capable of making these 90-degree turns, as well as navigating over weld seams and those types of things. But we have also integrated in with it a couple cameras, circuit board, a PCB, just so we can relay the live video feedback from the unit as it potentially navigates through this refractory slot. So we'll need to alter our mock-up with the refractory configuration that we have in there currently to this configuration so that we can see exactly where the unit might stall, if it does in fact stall, or if it can make it all the way to the central plenum. I think our unit can make the number of turns, but if it can't, we haven't tested whether it can drag that 37.5 feet with the number of turns with that all the way to the central plenum. We haven't tested that yet, so that'll be in the full scale mock-up. So we've got some videos here, upper right. You can kind of see the unit as it would navigate over weld seams. And then in the bottom center here, you can see the unit making these 90-degree turns, making multiple 90-degree turns. And so that's where it gets really challenging right there, when that cable starts binding on those 90-degree turns, and then you have multiples, so that's where it could potentially stall. But this unit has, roughly speaking, about 4 pounds of pull force. So I think I'm pretty comfortable to say that we could probably make the first two with this, maybe a third or fourth turn once we add the weight of the cable for that length for 17 or 18 feet. But we'll see just exactly how far we can get to the central plenum when we do the full scale test. And of course, again, this is just for the AY101 tank. It's the only tank remaining that has this configuration, and this system would be able to provide some sort of video feedback in terms of the health of the primary liner. Okay. I guess I'm going to pass the baton back to you, Glenn, real quick here, if you want to say something about the secondary liner inspections and some of the experiences you've had with that, and that kind of lays the groundwork for talking about this next particular tool.
Yeah, sure thing. So the secondary liner that we tried to inspect, like I said before, it's very difficult to get to, and the amount of inspection of the surface area that we can really take a good look at is very minimal, especially in the AY style tanks. It's either there's in the diagram, there's the edge drain, midpoint drain, and center drain. So we had come up with a kind of a bore snake style camera before, and using that, we were able to insert it through the leak detection pit, go navigate that 6-inch drain line, with the 4 sets of 90s and progress nearly to the center drain in that tank. The camera has the ability to look up and down, so we were able to look up some of those drain lines in the midpoint. But you can see our little our crawler that we used the first time around ran into some problems. Couldn't quite get enough traction once the drain line was pretty muddy, pretty wet, and so that kind of halted our forward progress. But we would like to develop another tool to do a similar inspection in our newer tanks that have a drain slot cut instead of individual drain line ports. So that gives us a swath, pretty much, representative look at the bottom of the secondary liner. It's pretty difficult to traverse a lot of the piping to get to that drain line slot, though. And you can see the challenge that they've got. There's a number of dissimilar sized pipes, dissimilar sized junctions, that go from a 6-inch pipe to a through plate, and that drops into a square slot. So we have to get in there and be able to get out. And if the robot dies for some reason under tank, we must be able to retrieve it mechanically using its tether. So that's a number of challenges that make it pretty difficult to design a perfect solution for this. But I think that's kind of sums it up.
Okay, thanks, Glenn. So one of the other challenges, or one of the approaches that we're taking, is a marsupial type system that can navigate through that 6-inch pipe that you see here, mating with the side of the refractory slot with concrete pad. And then once it reaches that end, to deploy another miniature rover type tool. And you can kind of see this is the primary slot that you see that goes from the outer radius to the central plenum. And you can see how it very, very slightly shown here, but you can see how the slot gets smaller and smaller and smaller. And then what we're going to have the system do is have the crawler crawl right up to the end and then navigate or deploy a smaller child rover, if you will, that could then navigate through this slot and then attach itself to the tank. There is another challenge here. You can see this word, this phrase here, tank gap. If we deployed a miniature rover that was just magnetic completely, it would have a problem trying to traverse this space right here, as there's just a huge gap, about 6 inches or so. So we've got our system that can navigate both on the ground of the slot, as well as once it gets closer to the tank slots, it can attach itself to it and then drive through these stocks. So here's a transverse slot that we're talking about here, shown here. So it would navigate through the slots at the bottom, and then reach up, grab the top, and then navigate on the top using the magnet. So I'll kind of show you that. But the biggest challenge, as Glenn mentioned, may not be having to cross these little gaps. It's just getting the crawler through the pipe. You can see all the gunk here. So that's something that we're going to have to work with WRPS on in terms of locking that up and making sure that our crawler can traverse through those challenges. So this is another sort of conceptual slide. That's sort of the concept that we had to get past this gap. But if you had the crawler actually mate with that concrete foundation, we would have some type of rover that could roll out and then use a scissor lift to attach itself, that has magnets on it, extend up, attach itself to the top, and then be able to drive down the spine of the drain slots, and then maneuver right or left and go through these other slots. That's the idea. So it's a marsupial type system, and then we'd have to develop some sort of housing that would house this and be able to deploy that particular unit. So what we've got here is a couple different videos. This is our 6-inch crawler navigating through. Let's see if I can. Navigating through an elbow, 90-degree elbow. And it works very much like a peristaltic crawler. It has these grippers on the front and back end and an extender in the middle. And as you can imagine, that the back end unit, this is a pneumatic system. The back end unit attaches itself to the walls. The extender extends. The front unit then grabs the walls, and then the process is reversed. The back unit releases. The extender collapses itself, and so you get this inchworm effect, and that allows you to navigate down. And since their space, or at least their length is defined such that they can navigate through these 90-degree turns, you can see how that would be achievable, that they could get through this. Now the problem is going to be setting this up so we can get through all that muck that you see in the bottom left corner. And Anthony Abraham and his team is coming up with ways to keep the unit sort of on the sides and locking itself on the sides, not necessarily so much on the bottom, so we can avoid some of that debris. So that's the big challenge, and locking that up is going to be even the bigger challenge. So here's an older rendition of our little scissor lift mini rover. Once we reach that area, then we can extend up. We can travel down either way, and then roll on the secondary liner or on the bottom. Either way, doesn't matter. And navigate back and forth. So that's our concept. And then of course this unit would also have to be have some sort of sensor that could then quantify damage, a UT sensor or some type. Then there's plenty of room. These slots are much bigger. I believe they're 6 inches wide. So we have a lot more room to add UT sensors or other types of sensors for interrogating the health of the structure. So let's see, then I'll shift gears here a little bit. That kind of takes care of some of the tank inspection tools. We have another task that we're looking at: autonomous surveillance of nuclear facilities and repositories. So the objective here really is just to combine the platforms that you can kind of see there to the right with the state-of-the-art for autonomous surveillance, and apply these in the nuclear facilities and the sites. So our current efforts is to develop these robotic systems that can navigate through the tank farm or other site facilities and automate the processes of surveillance by doing a couple different things here. We would like to come up with stochastic models to predict the overall radiation fields that are of interest by fusing a number of different types of data. In this particular case, some gamma measurements or imaging, surrounding imaging, 3D cameras, as well as LiDAR mapping. And so what you see there on the right, far right, we have, you'll hear me mention some of these terms. We have our Jackal, Anthony's a Jackal that was funded by the DOE MSIPP project. And he's got that instrumented with a number of different sensors. Difficult to see here, but he's got LiDAR and cameras pretty much along the whole unit, and it also has an arm that can reach out and grab things if needed. We have a smaller Jackal, bottom right here, with the yellow and black, that also is armed with LiDARs as well as 3D cameras. And we have a portable system over here to the further to the left, which incorporates all of those types of tools, and can kind of a handheld device, and can be integrated into other systems as well, backpacks or even on drones. And that's the idea, that we have a LiDAR that can do simultaneous mapping, 3D mapping, and I'll show you some examples of that here in a second. So this is a pretty busy slide here. I got 4 different videos to show you that kind of demonstrate the concept. Up here in the upper left, I know it's kind of small, I apologize. Let's see, but you can kind of see here as on the far left of this little tiny screen, we have 4 different cameras that are being used for this Jackal as it navigates around in a corridor type environment. Taking LiDAR measurements and superimposing that LiDAR measurements with, pause these other ones, I think they're all running simultaneously. But they're doing simultaneous mapping, and then or 3D imaging and the LiDAR mapping, and then superimposing color on the system, so you can kind of visually see and then get distances and all those types of things that would be very useful for understanding not just the positions of where things are, but the state of how things are. And then we can also add other types of sensors, as mentioned before, thermal sensors or radiation sensors to assist in that map. On the second one here, similar configuration with the jackal. It moves as it's showing as it's moving down a corridor, doing the same type of thing, taking LiDAR measurements and then color coding them with the 3D imaging. So you get a little bit more realistic picture that with distances associated with that. And kind of see how the point cloud is being populated and then color coded. And then on the bottom here, we have a simulation tool. It's just kind of simulating the same process, but allows us to, go create a virtual environment so we can test algorithms and that type of thing for evaluating ability to autonomously navigate plus do a 3D map. So that's something that is very, very good. We can utilize all the tools that we test in that virtual environment on the actual systems themselves. And the big picture here is the jackal, and you can kind of see our jackal here. We have the 4 cameras. Let me pause that one. We have the 4 cameras showing our jackal navigating around in our lab, and then out a corridor. You can kind of see it. It took some pictures here. Actually, let me back it up here. So we don't have any information. And then as he's scanning around, you can see how the point cloud's populating the entire area, and then color coding it, or color mapping it, and then he navigates into a hallway, and you can see this as it's live happening. This is all done autonomously, taking images and then incorporating those with the map or with the LiDAR data. Okay, then shifting gears once again, we have another task that's related to our the Savannah River H Canyon facility. The Savannah River has this facility that is the remaining, only remaining plutonium reprocessing facility in the U.S. It was constructed in the 50s, and part of that facility includes an exhaust tunnel that's been in operation since the 50s, made of concrete. And one of the concerns is its structural integrity, as it must exhaust. Actually, all the exhaust from these the facilities gets thrown through these exhaust tunnels and goes through a filtering system. So it's very important for these to remain operational. But they've been operating with for about 60 years or so, or even longer, 70 years now, degrading the concrete walls with acidic fumes as well as radioactive fumes. And so part of our next task was really to sort of help develop tools that can help understand the degradation of those walls. And I've got a couple different slides here. You can the exhaust tunnel itself is around, I think it's 10 feet by 10 feet in area, and then goes a couple 100 feet in length. Some sections have large pipes. And then typically humans cannot go through these tunnels to do any kind of inspections or repairs. That's not even feasible. And what they like to do is they like to send autonomous systems here, robotic systems through these pipes, and then do some inspections. And as you can see, there's a 3-foot diameter pipe to the left that's no longer functioning, but it's non-magnetic. And they like to be able to see and see behind that and make some assessment as to the structural integrity of the tank, or sorry, of the exhaust tunnel walls. It's made of concrete. Some of the areas it's got up to 2, 3 inches, 4 inches of exposed material, and rebars exposed, that type of thing. So we've developed a couple different tools that can navigate both on the pipes as well as up the walls, to potentially assist in quantifying damage, as well as maybe even doing some repairs. So that's where we're going with this. And we have the concept here is to use a ducted fan that you see here to the right with on a platform. And the ducted fan is used basically to adhere the unit to the wall, and we'll kind of demonstrate for you here in a second. So we can also curve the chassis, and so you saw that big pipe, 3-foot diameter pipe. This is a ducted fan that's basically blowing flow out, creating a normal force to the system, so then it can navigate around these pipes, and then provide some information, whether it's visual or potentially even doing some sort of quantitative inspection. But the idea for this one was just to get around the pipe so that we could see on the opposite side. And of course, the system can carry its own weight as it goes upside down or on top of the unit. The other part of this was to potentially have, and these systems would be deployed from some sort of mother robot, as I mentioned, that would navigate through the exhaust tunnel. And this unit can traverse both axially or along the radius, along the axis of the pipe. Either way, it can navigate back and forth. And to the right over here, we wanted to potentially develop a tool that could be placed on the walls for helping assist with maybe doing some sort of quantification and repair. So we have a unit that can navigate on the ground and then traverse up the wall, transition to the wall, and then traverse up the wall, and navigate over pretty rugged terrain, so to speak. So you can see how that would work for this smaller particular unit that could be used to help quantify damage if needed. So we're running a little late on time here. Sorry, Walter. I'll try to speed it up. So one of the other things we were trying to do is the repair aspect of it. And the previous unit you saw was pretty small. So what we've done is we've developed a larger unit with 5 ducted fans. And under that unit, we would potentially have a sprayer type device that could potentially apply some sort of protective coating. And so I've got some videos here. This is a 5 ducted fan system, and you can see how it can transition from the ground to a wall and navigate up that wall. We're in the process of developing this system now. And then in the end, what we would have to be able to do is integrate this frame that you see, this XY frame, that could potentially apply some sort of coating on the walls to protect it and keep it from degrading any further. So here's an example of how that would work. And that unit would be placed underneath the chassis of the wall crawler. Okay, now we'll transition over to our LM task. Leo, I don't know if you wanted to comment a little bit on this for this.
Yeah, no, sure, Dwayne, no problem. So pretty much, as Dwayne mentioned, the other surveillance, remote surveillance project that we're doing for EM, we're applying similar technologies and techniques and robotic systems and sensors, LiDAR type of systems to DOE-LM site, so legacy management. So again, the objective here is to evaluate suitable remote sensing imaging technologies and methods to evaluate the different environmental characteristics represented at the LM site. As you know, LM will take over EM once the mission has been completed. So a lot of the waste that will be buried at those sites will have to be monitored for many years to come. So we have to take into consideration even long-term effects of climate change to the various sites across the country. So to do that, we're working on similar systems of robotics platforms, whether it's a drone, a ground platform, four-wheel drive vehicles, all kind of deployment mechanisms where we can integrate those with sensors and collect information about the sites for years to come. For example, we're looking at the land use, the covers, erosion problem that may happen, perhaps due to climate change, vegetation, surface hydrology factors, even the wildlife migration patterns. All of those things would have to be, surveyed in a consistent basis. And to do that, we are investigating new technologies such as, drones with a bigger payload that can carry various sensors, photogrammetry, LiDAR, 3D cameras, as well as state-of-the-art sensors that can detect to the level of detail, for example, the digital elevations or factors like that might influence how we continue monitoring the sites. And once we see a change, then we can go and repair the covers of some of the waste disposal sites, or some of the environmental conditions that may take place in the next 100 years, 500 years. So we're applying similar technologies as the one that Dwayne showed in the previous slides to address legacy management sites. And I believe we have one video coming up in the next slide, Dwayne. I think this is a survey that was done at FIU. I think on the left side, on the top two figures, you see the FIU parking lot, College of Engineering, where student LM fellow Eduardo using one of our drones, and he's been surveying the parking lot basically of our school here. I think that's a student parking lot because it's not paved. So that tells me that is the student parking lot, as opposed to the faculty parking lot. But there is a truck that's been standing there for I think since last year. So we are surveying the car, the trucks, and some of the features of that land, and then continue doing so for repeatedly until we get a good representation of that site. And then in the future we'll do the same and see if detect any changes of the site. So similar techniques are being considered for this summer, where Eduardo will go out to a LM site or sites, and he'll take the drone and some of the techniques that he's using. In this example, he's using the photogrammetry mapping of that area. So this is going to be deployed at a LM site this summer. The same drone and the same photogrammetry techniques, and also a LiDAR is projected to be deployed as well. Go ahead, Dwayne. I believe next slide. And yeah, this just shows the type of LiDAR imaging that we are developing as well, the 3D point cloud, and using the various drones that we have at our facility, and generating the 3D mapping of the sites as well. Go ahead, Dwayne. I believe I think that this might be the last one. Very quick. I know we're out of time.
Sorry about that.
Yeah.
Sorry.
This is another project that we did under the DOE EM MSIPP collaboration with Savannah River National Lab, Idaho National Lab, and Florida Atlantic University. And this is just the automation of glove box work. So people that are working glove boxes, you have the 3Ds, dangerous, dull, and hard to work through those gloves. Excuse me. And I don't know if you can play the video, Dwayne.
Yeah. All
right. But really what we have done is using a universal 5 robotic arm integrated with the prosthetic hand, and really duplicating the type of work that a worker will do on a consistent basis or a daily routine of a worker working through a glove box. It's repetitive. It's work that is dull. So in terms of using, perhaps this robotic system can aid the human in terms of using some of those tasks that are repetitive that perhaps a robotic system can do, and then the worker can do other tasks as well. So we did this work for a couple of years, and the next phase of this, or the second phase, was to develop exoskeletons to be used by the workers. So in the forearm and the hands, developing some exoskeleton that facilitates the worker in terms of the stress on the hand or the stress on the wrist while they're doing this type of operation, so they can prevent future injuries such as carpal tunnel syndrome. I think that's the one for that slide. And go ahead, Dwayne, if you want to take the last one.
This is just, I think we've already kind of alluded to this, but what we do is we take at FIU, we take ideas, we work them out in terms of the proof of concepts or the design stage. We prototype. We do an in-house evaluation, and then we kind of try to do a deployment on some level in-house, and so with the overall goal of trying to get our units deployed at the site. So you can see this is sort of a timeline of our thought processes for our mini rovers, the UT rovers, 90-degree rovers, the marsupial system, our wall crawlers, as well as some of the platforms for WIP and the LM sites. You can see this basically maps out our thought processes for trying to get these systems from initial states all the way to being a deployable state. And that pretty much wraps up the presentation. If you have any comments, questions, and then I think Walter, you wanted to talk a little bit about the next tech talk.
Thank you, Dwayne. I appreciate you and Glenn for presenting this. I just want to give the opportunity to anybody who has questions regarding this topic. I know some join a little later. If you have any questions, please take the time. I know we're scheduled to 2 o'clock, but we have time to answer any questions before I go into other things. Well, you're being a quiet audience today. Not a lot of questions, or that you can't hear us.
Yeah, we've been on mute the whole time.
Yeah.
So,
okay. Well,
so Walter, just very quickly, I wanted to welcome our colleagues from headquarters, and Jennifer and Jania, JP. Thank you for joining us this afternoon.
Can you hear me?
Yep. Go ahead, JP.
Yeah, I have another meeting. I have just one question. The last slide, the exoskeleton, is that the one that you're planning to work with Sandia?
Yes, that would be the
Okay.
idea. Yeah.
It's the first time I mean, maybe I saw it before, but first time I see the.
Right. So FIU you've been working on this type of glove box issue in terms of using robotic systems such as the Universal 5 and the prosthetic hand. And also after that, we also worked on exoskeleton that are placed on the human. So it facilitates the movement of the muscles and alleviate the muscles and for the workers in the various tasks that they have to do.
Have an exoskeleton. I know that you got the glove box, but what about the exoskeleton? Is that something that who is providing that, or you already have something?
Yeah, we do. Yeah, we do a couple of prototypes that we have already developed, and that was developed toward the end of the MSIPP project that came to an end last year. So we're transitioning those onto the Sandia project.
Perfect timing then. Good.
Yeah, perfect timing indeed.
Hey, good presentation. I have to step out, but yeah, I joined a little late, but I like what I hear. So.
All right, thank you, JP.
Good as always. Thanks, Leo.
Thank you, Jania and Jennifer. Thank you.
Just a quick reminder that the next Tech Talk is scheduled for July 20. If you can go to the last slide. And Himanshu actually is going to be part of that. So Himanshu, if you're on the line, would you mind kind of just elaborating a little bit more on who's going to be the collaborator and
All right, thank you, Walter. So the next Tech Talk on KMIT platform will be focused on Advanced Environmental Monitoring System, ULTMS, a new paradigm of long-term monitoring. This will be presented by Dr. Haruko Wainwright. She's a research scientist at Lawrence Berkeley National Lab and also an adjunct professor in nuclear engineering at University of California, Berkeley. Her research is focused on environmental informatics with emphasis on stochastic hydrology and special statistics. She is working with an ULTMS project and supporting the long-term environmental monitoring at Savannah River site. So she will be talking about this project during the next presentation, which will happen on July 20th.
Thank you, Himanshu. I appreciate that. It's just a reminder that we have a feedback form. The link is available right there. You can go to scan the QR code on your mobile device and fill it out. It should take less than 30 seconds to fill up. And also, this meeting was recorded, so the recording of this video will be posted to the website, Tech Talk website, in the next couple of days. If there are any other final questions, I'll be happy to answer, or otherwise we'll conclude this session.
All right, very good. Thank you, Walter. Thank you, everyone, for participating, and of course, thanking the presenters, Glenn and Dwayne. Thank you, guys.
Thank you.
Well, this formally concludes that the video is going to start recording, and thank you for attending the Tech Talk. We'll see you next time on July 20th.
Thank you, guys.